medical image processing, geometry processing, and now during the PhD, I am also pursuing PhD at IIT Delhi now. So I'm looking into rendering. Okay, the session is being recorded. Is that so?
Yes, sir. Actually, that is the requirement of the ICT. We have to put this on live YouTube channel. So we are just recording this
I
session.
see. Okay.
Is it
Okay,
okay,
then.
sir?
Yeah, that's fine. I wasn't aware. All right. Uh, yeah. So, yeah. Then I need to share only the public material only. Yeah. Yeah. So that is about me, and currently I'm pursuing my PhD at IIT Delhi, and I am also principal engineer with Stryker Corporation. This complete session is yeah. There will be some is coming out of my experience in industry as well as in academia, but I am here sharing with you as a student of IIT Delhi. Yeah. There will be no private items or proprietary software or any data being shown or shared during this time. All of my material is based on research papers or lectures available online, and as well as the data that we use is public data from University of Utah. Uh, and the application that I shared with you is MITK. It is again an open source application. Okay, so let me share my screen now, and we will start from there. Yep. Okay, can you see my screen now?
Yes, sir.
Okay. As far as conducting of this session is concerned, I believe since we have quite a lot of time, about 2 hours or so, so we can keep it interactive. Whenever you have a question, you can ask me. I would try my best to answer. If I don't have any answer, I will just note it down, your question, and I will come back to you later on, or we can take any difficult questions by email later on. Uh, yeah, and so we'll keep it interactive, as well as there will be a couple of breaks during the sessions of about 5-10 minutes. Speaking for 2 hours or so is will be difficult. I believe you understand that, and yeah, that's all about the session. Uh, so before you were joining, I had shared 2 links with you. One is this SEI head model from University of Utah. Uh, if you open the link that I have shared in the chat, you will find that there are multiple data sets, T1 MRI, T2 MRI, TWI, and so on. So right now, just download the first one, which is T1 MRI dataset. It might take a couple of minutes or so, depending upon the size of data. I have had already downloaded it a few days back, so I don't know what is the size. And additionally, I have shared another link of an open source software called MITK, stands for Medical Imaging Toolkit. It is an open source software from German Cancer Research Institute. You can download it for Windows or Linux based on your platform. I would prefer that you download the zip archive or the tar.gz if it is Linux. Then unzip it and just keep it as it is. If you want to install, then yeah, it sometimes it's hard to have so many softwares on computer system. So I would recommend that you can leave the installer actually and just use the zip archive. So these are the 2 things that I will be using. And since we have quite a lot of time, so we can you can as well look into this application with the data. I will be showing it to you how to use it. So side by side, you can work along. I'll go a bit slow so that it can be done. Now coming on to the customary slides. Yeah. I will also switch off my video now since it's just a screen and all. All right, so the topic of discussion today is the 3D visualization methods for medical imaging. Yeah, we will be talking only the 3D visualization methods. There, one can visualize medical images in 2D, but there. So so setting up context here. It will be just the 3D visualization methods. About myself, I have overall 14 years of experience, primarily in software development. Currently working as principal engineer with Striker program, and I am pursuing PhD at School of IT, CSE Department, IIT Delhi. I have some exposure to geometry processing, image processing, and computer graphics, and I use all of these, the knowledge that I have gathered from these fields and the knowledge of software engineering to implement patient-specific solutions. By patient-specific solution, I mean that, for example, an implant that is specific to the bony anatomy of a patient. So everyone has a different size. Everyone is of different shape and size. So then their skeletal structure might differ a bit. So then if we create an implant or a visualization that is specific to that patient, then we call it patient specific. Yeah, on the right hand side, just for fun, I have added this GIF. It is a very popular 3D model, uh, but here I am trying to show that I work in this area of geometry processing. Geometry processing implies that mainly these triangular meshes, these are created maybe via laser scans or from medical data. So today, uh, the surfaces that we will reconstruct are from medical imaging data. Here, the one that is being shown here, the 3D surface for may be reconstructed from a laser scan. Okay, coming on to the agenda. So first, I will give an introduction about why are we going to discuss these and the medical imaging modalities. Since you are not from a medical background, even I am not, but it is an interdisciplinary work and we keep on learning as we progress in our careers. Uh, so there will be a little bit of introduction into medical imaging modalities. Then we will discuss about surface rendering. Oh, mainly we are going to discuss about rendering in medical imaging, and that can be categorized as surface-based rendering or volume rendering. And that's all. We will also be uh, using a software that I already shared, and uh, so all of the stuff that we discuss, we are likely to work on it as we go along. Okay, so first of all, talking about a surgery. A surgery can be divided into three parts broadly. The preoperative or the timeline of a surgery can be divided into three time zones. The preoperative, the intraoperative, and postoperative. Preoperative is something that comes before surgery. Um, so here the health records of a patient are seen, and the medical imaging data, that is X-ray or CT scan, that is gathered, and sometimes based on this information of X-ray or CT scan and or MRI, 3D models are created, or even some renderings are created so that surgeon has more information and he can simulate. Maybe he can do some pre-surgical analysis. He can do the surgery rehearsal if simulation software is there using the actual patient's data, or he can just go through the 3D models and align his mindset what he is going to see during the surgery. So mainly this medical data information gives him more insights to what to expect during the surgery. A surgery is an art, as the surgeons say. Um, there are quite a lot of variables that happen during the surgery, and one of the important uh, uh, point or knowledge point that I understood or have learned in while working in medical imaging data is that do not force technology onto surgeons. So we should be aware about, or the doctors. So mainly we can say medical practitioners. We should not force whatever technology we have invented onto what the surgeons are doing. It is important to understand what they go through during the surgery or before the surgery, in order to understand the context as well as what they want to do. Then only uh, provide certain software technologies that are relevant for them. Yeah. So now coming on to intraoperative, here the patient is monitored. He has been anesthetized and prepped and draped, and the operation is performed. So that is intraoperative stage. And post-operative is that when he is shifted to the post-anesthesia care unit and is monitoring. Then later on, when he is out of hospital, the recovery monitoring. A lot of research has gone in the pre-operative and intraoperative. Post-operative is something where still a lot of work needs to be done. And in India, I believe it's much required, or I mean, we are at a very low end of it. So the post-operative would be essential to understand how a patient is recovering after the surgery or after any procedure. So this is about the stages of surgery, and there are other technical terms that are discussed uh, in medical practice. Is first is diagnosis. So diagnosis is something, or it is can be said as the methods that a doctor uses in order to tell what disease it is. And so, for example, he might use MRI scans and CT scans to tell what the disease is, or even the blood sample results like uh, blood count, WBC, RBC. That is all diagnosis. And then prognosis. Prognosis is about how the disease will progress. So telling from the data or from images or with his experience how a disease will progress. That is called prognosis. So these are the areas where 3D medical visualization can be used in diagnosis, and in prognosis, and in education. So in education, for example, when um uh, the the doctors, they just start studying, and then anatomy education is one of the first of the subjects that they study. Usually it happens with the help of atlases. Atlases are sometimes books or sometimes models, uh, and then they just see that. So if we make a 3D interactive atlas, so then that it will be easier for them to learn. So they will get more information about how spatially the organs are oriented. So that will have a less cognitive effort for them. And how so it can be done using just by seeing the 3D models or by surgical simulation as well. Surgical simulation is a superset of this application of anatomy education, where not only in addition to looking at the anatomy, a doctor can experience the touch as well. So a lot of work has been done in this area. A lot of neurosurgery simulators are there or otherwise for other anatomy, where they can even interact and feel a certain organ and see it as well. So there are two parts to it: haptic rendering, which gives the haptic feel, the sense of touch, and the visual rendering. Today we are going to just discuss the visual rendering, not the haptic rendering. So yeah, so uh, the application area for 3D modeling is education as well. Now, it can also be used during the pre-surgical planning. That is, before the surgery, as a patient's data is taken, and then 3D models are created, and then the surgeon is planning for a surgery before the surgery. Yeah, so that is pre-surgical planning, and then he can as well use these 3D models to discuss with other surgeons that, for example, he wants to operate in certain area, then he can ask some other expert about some other organ at whether his approach is correct or not. And additionally, he can talk to the patient himself. So patient might not be able to understand the radiology scans, but it might be very easy for him to understand it using the 3D modeling or 3D renderings. So he can discuss with the patient and get much better idea about um what is going to be done with the patient, and in one where a dissection would happen, and what is the problematic area in the body. And then they can rehearse as well. Neurosurgical simulators allow surgeons to rehearse a surgery before actually doing, or even these are used for training. And surgical navigation. So surgical navigation is an intraoperative stage item where while doing the surgery, there are 3D cameras that track the patient's tool uh, so there is also 3D renderings available. So by virtue of tracking and registering the tool with the camera, with the help of camera to the virtual data, uh, a surgeon is guided where he is cutting or where he is maneuvering in the patient's body or outside. Yeah. So this gives him more insight to yeah, more information to conduct a successful surgery. The idea is that there should be least possible tissue removal or least possible blood uh, loss, so that later on recovery of a patient is much faster. Okay, so this is about application. So here all we use 3D medical visualization methods. Now coming on to what all or the term used is called modality. What all modalities are there to get the imaging data so that which can be then rendered in 3D. So yeah, so there are a lot of imaging modalities. It can be just a camera, for example, microscope or an endoscope. It can be an X-ray film, which is just a single slice. It can be ultrasound, or it can be nuclear medicine. In nuclear medicine, a radioactive substance is injected into the body, and then a scan is done. So, or it could be CT. In CT, X-rays are used to construct, or the full form of CT is computed tomography. Uh, so here, so I have highlighted these two imaging modalities here because we have this data from the source that I shared with you, and I'll be discussing more about these two modalities. So CT stands for computed tomography, and uh, yeah, so it uses X-rays to get a number of slices from a certain region of interest of a patient, and then 3D model can be constructed from it. And MRI stands for magnetic resonance imaging. Here, magnetic field is used to construct the uh, image slices. MRI is based on different CT uses X-ray, so it is based on the absorption principle. So wherever there is uh, so for example, CT is used for bony anatomy, and MRI is used for soft tissues. Soft tissues have water content, and then when they are subjected to magnetic field, the water molecules, the water atoms, no, it's a molecule, orient in a certain fashion, and then that allows to get an image from magnetic field. Yeah. So the working principles are different. CT is harmful. MRI is not, because MRI uses magnetic field. And CT and MRI, the typical resolution is like 526 cross 526, and then these number of slices can vary based on the length that is scanned, can be typically from 3060 to say about 200 300. And then these all imaging modalities are used for certain analysis type. For example, structural examination. So when you see the structure of anatomy, how the organs are shaped, then only CT and MRIs are used. There are, of course, a micro CT available, but today we are going to discuss only about the structural aspects. We will not be discussing the functional or metabolic aspects. Like, for example, there is a variation of MRI called fMRI. fMRI stands for functional MRI. It uses the oxygen concentration in brain to tell the active area of brain. So it is used a lot in research um, for analysis of brain activity. But we are not going to discuss the functional imaging modalities. We'll just study about the structural. Now, coming on to a little bit detail on CT scan. So the machine looks like somewhat as is shown in the picture on the left. And when visualized in a software that I had shared, the MITK, it would look like this. So maybe this is the time I load a CT scan and show you how it would look like. So after you have downloaded MITK, so these will be the few directories there, and in the bin you'll have MITK workbench dot executable. So you will get these directories after you unzip. So a question to everyone: have you downloaded it or no? So I can see some raised hands or so. Or you would just like to see as I progress? I don't see any reaction. So looks like no one has downloaded it. Is it so? Okay.
Yes, sir. So far not downloaded.
Yeah, so okay, maybe then I will show you how to do it. You download it from here. If it is Windows, just click on this button on the downloads, the link that I have shared, and then you will get a zip archive. Copy it somewhere, for example, a workshop directory, and then unzip it. So then you will get this kind of folder. Within this, go into bin and then workbench. Now let me just run it. Oh, it was already open. Okay, so this is how the application looks like. And we are going to open the data in this application. So I have this from SCI Utah. I have a downloaded T1 dataset. There is something called nerd.nrrd file format. I am going to open it here. So by the way, I wanted to show the CT scan or the MRI. So they have also created a pseudo CT. So I'll just open it. Okay. So just talking about this application. So this is there are a few terminologies that are used in medical imaging visualization. They are axial. Axial is as if you are looking from the top of the scans. So as I am scrolling through these slices, so they are one above the other, one slice above the other. So they give you uh, a feeling of that it is like continuous, but they are discrete slices, and then interpolation is there between various slices. We can see that by looking at, so there is each pixel of this size. Similarly, in y direction also we have the pixel. So this is one slice with certain intensity. Okay. So actually the right word is voxel, volumetric element. Okay, so I was talking about various terms. First is axial. Axial is as if you're looking from the top, and by mouse scroll you can go through different slices. And sagittal is as if you are looking from the side of the body, and coronal is you're looking from the front or the back. So yeah, so these are three orientation, and the slices are produced from it. And in the 3D, we will see the how if we have a 3D model, so that will be seen here. So this is the minimal detail about these display windows that you see. And you will see, you'll observe that in an X-ray, the bones, so here the skull, that gets that has higher intensity value as compared to the soft tissues that are inside. Yeah, so that was about CT scan. Now coming on to MRI. Yeah, so I've already shared these links for you to experiment. Now, similarly, we have MRIs and where magnetic fields are used to take the scan. And here is a patient lying and his head is being scanned. And on the right hand side, you see a snapshot of a T1 MRI. You will see the soft tissues inside. So this is the cortical surface inside the brain. So similarly, I can go and I'll close a project that had CT scan loaded. I will open the MRI. So yeah, so we have the MRI data. Just the same like slices. There is axial, sagittal, and coronal. Just that the structures that we are able to visualize now are soft tissues instead. And here you can also see the position, like it's the coordinate XYZ coordinate and also the slice index. So for example, wherever this this crosshair is, these lines, these are called crosshairs. So it tells the location of the crosshair. It's at 110 in X, 135 in Y, and 175 in Z. So as I move it, you will see that X, Y's are changing, but the Z is remaining same because I am interacting in the axial display plane. So this is about the visualizing medical data, CT and MRI in the MITK application. You can as well go through these by the help of these sliders here. These applications are written in C++ and Qt. Now we'll go into more details later on. Going on to next slide. Yeah, so I have already given a demo. Now, you already saw that the image, we have these image slices, which are essentially a number of images stacked one over the other, and then we see those here like this. And these can also be represented in as image volume. So then you can consider that this is, so when stacked one over other, so the space between one slice and the other slice is interpolated, and then that forms a voxel. So if you see here, so this is a voxel. This is a three-dimensional element like a cube. So if it was scanned in, so here we can see the details of this image. So it is of dimension 208, 256 cross 256. So it is, yeah. So in that's why we are seeing these are like cube. But if the resolutions were different, that is they were anisotropic, then they will be parallelopiped. And then yeah, so this is about, so we can imagine that as if it is these are voxel elements stacked together one over the other, and are being rendered in the 3D space where each voxel has certain intensity. So yeah, so this is what I wanted to say. So it is like a big brick where there are small cuboids or cubes of voxels, and each voxel has a certain intensity value in the scale range of 0 to 256, which here is a grayscale value. So that allows us to see it. Yeah, so the next topic that we are going to discuss is surface rendering. That is going to be quite a long session. We can take here, it's already 40 minutes or so. So we can take about 5 minutes break and we will resume from surface rendering. Is it fine?
Yes, sure.
Yes, sir. Definitely.
Okay, so right now it is 7:40, so we will meet at 7:45. You may as well use this time to download the software if you haven't, and the data.
Uh, Sir, is it okay to ask a question during this time?
I think sir is not there.
Okay. Yeah, I see a raised hand. Is there any question?
Yes, sir. Can I ask a question?
Yeah, sure. You go ahead.
Sir, I was using one of the tool. Uh, that is ITK Snap.
Okay.
I just feel that like this is having some of the different modalities than ITK Snap. For visualization, I'm using ITK Snap.
Okay.
So, which one is better? Can you suggest, sir?
I have not used ITK Snap a lot. Yeah, under the hood, MITK also uses ITK. So
Huh.
I think MITK has much more functionality and is still constantly being developed. Yeah, I need to check what the comparison between the two tools. I will just say that I have more experience in MITK. That is why I'm using it here, and it has quite a number of functionalities that I want to show.
Yes, sir. Actually, sir, I was going through it, and in tutorial, I have seen that you have worked on this MRI diffusion part also. That's what it shows in the some of the areas.
MITK, yeah, it shows it has that implementation as well. But today I'm not going to talk about that. I'm also not an expert in that area.
Okay.
But if you are comfortable with ITK Snap and it provides all this functionality of surface extraction, segmentation, and surface visualization, it is totally fine to use that tool.
Yes, sir.
Yeah, so today, if you are using it, maybe as I talk through it, maybe it is also an opportunity to learn about it, and then you will be yourself able to tell where it stands and as compared to ITK Snap.
Surely, sir. Yes, sir.
Yeah, and is there any question from anyone else? I believe all of you are faculty members and you like that students ask questions. Somehow the roles are reversed today, and maybe if you have any question, I would really like to answer. If I could. Okay, then if you don't have any question, I will ask a question. That's funny. Okay, so we discussed about this slide. So and then there are voxels. They present in 3D space, and they have some intensity value. So what kind of field is it? Is it a scalar field, a vector field, or a tensor field?
Sir, I think it is a vector field.
What is the reason to say so?
I don't know the reason, but because it's a dimensional voxel, so we mathematically can call it as a vector.
Sir, may I, sir?
Yeah, sure.
Sir, I feel it's a tensor field because mainly like we consider the distance from each other over there, sir. And we also need to understand the relationship that is in terms of say the stress strain in a way.
Oh,
So
okay.
that is a tensor field.
No, okay, yeah. So here we are not going to understand that. If that was the case, like stress or strain, then you could consider it tensor field. But here it is just the intensity values. So these are scalar values in space, in
Yes,
3D
sir. In that,
space.
yes, sir. Yes, sir.
It is a 3D scalar field. So MRIs and CTs allow us to get this 3D scalar field. Because these are just some numbers in 3D space. There is no direction to it. So that's why they are scalar. So now we'll talk about surface rendering, and this requires that we create a surface from this 3D scalar field. Usually the term that is used For I hear an echo. If you can mute yourself. Okay. Yeah. So I was talking about 3D scalar field and then isosurface extraction. So isosurface means that extracting a surface where the voxel intensities are all same. So just like iso contours are in 2D, so isosurfaces are in 3D. And we would be extracting isosurfaces from this voxel data, that is this 3D scalar field. And there are various methods to do so, and we'll be going to discuss that in our next section. So coming on to surface rendering, obviously, if I want to render this, so now we have slices, and or I can say this 3D scalar field, and each at each location there is some voxel intensity value. But how can I see it in a better way? Can I extract a surface from this voxel field of the area of interest and then I just visualize that? So that is what we are going to discuss here, how to do that. So yeah, so where do we use surface models? So surface models can be used for diagnosis. For example, for the brain, the angiography allows us to get the image of vessels in the brain, and then creating surface from those vessels, one can tell about the brain aneurysm, that where is it uh, is it really what is the stage of it, maybe I cannot say about stage, but how difficult would it be operate there. And so yeah, brain aneurysm is something like a spherical protruding that happens on the surface of vessels that if got ruptured can lead to stroke. So yeah, it can lead to this brain hemorrhage. So yeah, so or for this intervention planning, so for planning the surgery, surface models can be used for medical education if we have surfaces for different uh, anatomical organs. So then we can talk about the shape and where it is located, especially for biomedical simulation as well. These surfaces can then be created. One can create volumetric meshes as well, and then use it for biomedical simulations. And rapid prototyping, in the sense that once you create a surface, you can also create 3D print from it. So let's talk about surface creation first. So when we get the image from a CT or MRI, there are times when there are noise or the quality isn't that good. So that requires one to do some image processing, apply some image processing on the CT or MRI slices. Those could be noise reduction, for example, reducing the noise of the images, edge enhancements, or contrast enhancement, or even applying morphological operations. I believe you know all these terms, and I will not be going into details of image processing, but mainly after having got a clean data. So these image processing methods allow us to clean the data, but we should be aware that we are not changing the given image quite a lot. And whatever operation that we do on the image is somehow able to maintain the accuracy of the region of interest. Yeah, so I'm not going to discuss details of image processing methods. Maybe I'll just show an example. Here you see that on the left hand side there is an image, and there are, maybe you see here are some noise areas. Noise, maybe it is not relevant for us. That's why we can call it noise. And then using median filter, this goes away and the image is smoothened. So we are using median filter here to get a better image. Now, once we have once we have done this image processing algorithms on the images, usually what happens is that these scanners that are there in the field these days, Siemens, GE, or any other scanner, they provide a suite of image processing tools already. And also over the time, the quality of images that are that we get from these scanners has improved. And that's why there is maybe lesser image processing post after getting images, the post processing is required, or even if it is required, sometimes they do it in an automated way. There are some standard ways, some standard methods that they do follow for when a certain protocol is chosen for image scanning. Usually all of these scanners have certain presets. So when a person uses this scanner, the computer that is attached to this scanner there in an application running on that computer, they have presets that are that can be used, and that allows us one to get relevant image for relevant type of procedure. Yeah, because setting these parameters can be mind-boggling or challenging. That's why presets are there. Now, once we have the image, in order to create the surface, we would like to first segment our region of interest. So what is image segmentation? Image segmentation is just that we separate out our region of interest from the rest of the image. We apply a label to that voxel, and all of the voxels that form one component or one region of interest will have same label. Rest components of the image can have different labels. By labels, I mean that, for example, there is an image for which the intensity values can range from 0 to 255, and then we create a mask which is of the same size of the image, and then we can paint. We can do this manually. So while looking at the image, we can paint certain voxels in that mask that we consider is of interest, and that will have only that one label. I'll be showing it as a demo to you. Yeah, so maybe I'll just jump onto demo and show you how image segmentation is done. So today we are going to do it for medical images. I have this MRI loaded already, and if you see in this application, there is this image segmentation tools, and I have opened image segmentation tool here. Now, in order to do the segmentation, we first need to create a mask. I'll just say, okay, I can just create it from here. So I've selected the image T1 corrected here in this plugin or the segmentation tool. Then I create a mask. Now I have a mask which appears as a child for this image, and now I can paint in this area. So all of these tools become active as soon as my mask is created. So mask is like a scratch pad. Now when I paint, I don't actually change the voxel values of the image, but I paint on this transparent mask which is here. So it is present here, but it is totally transparent. That's why we just see the image, but not the mask. Now, as I said, the first method of segmentation can be the simple manual paintbrush tools. So, of course, it is quite manual and can take a lot of time, but it is still used quite a lot with the advances in deep learning and all, and especially in radiology. You would have seen everyone is actually implementing or creating deep learning algorithms for segmentation of image data. So there has been quite a number of advancements. MITK, this toolkit also has some library that allows to do automated segmentation, but today we are going to discuss automated or semi-automated methods, but not the deep learning methods. Okay, so for example, I'll just open this paint tool. I've opened the, there is 3D tool as well as the 2D tool, but let's say I open the paint tool, a 2D tool, and then I can increase the size of my brush. And I can go, for example, I just want to segment out maybe which area. Yeah, let's first close and go to the region of interest. Maybe I want to segment maybe only this region. So I can open the paint tool, zoom it, reduce the size because it's a big size, and then just paint the voxels. Now you see that. So I'm doing a bit rough segmentation, and this is how I can paint. So you have the segmentation on one slice. Similarly, you can go on doing in other slices and so on. But as you can observe that this is quite a cumbersome method and it will take many hours to actually segment. So that's why we have sort of semi-automated methods. You can as well remove it by using this eraser. So if you do some mistake, you can erase it. Okay, now let's talk about other methods. And then there is there can be contour drawing methods. So yeah, you can. So here I just showed you the brush. You could as well add a contour, maybe, for example, like this. So yeah, it's just somewhat easier. If you're sure about what largest area you want to segment in one go, you can draw this contour and have it. So these are purely manual methods. And then semi-automated methods. So we can classify segmentation methods into 3 types: manual, semi-automated, and automated. Now coming on to semi-automated methods. Example, I open this 3D tool and I open the thresholding. So upper lower, UL stands for upper and lower threshold. And I zoom out. And now I want to say maybe I'm interested in this brain. So I can change the threshold values here. You can see that based on the, so this provides a range of voxel intensity values. So our voxels are ranging from 424 to 11294, and I am just choosing a range in order to just segment the area in which I'm interested in. So after I'm done, I can just save this or lock it. Yeah. So this is how thresholding tool works. Here you observe that it is sort of semi-automated. You are not going to change. You're not changing or painting on each slice, but just by virtue of this slider, as you change the slider, the algorithm just parses each voxel of this image and sees whether it is within this voxel, within this Hounsfield, within this intensity value range. Then it just paints it. Otherwise, it just leaves it. So that is how it is done. And of course, you can see that you were interested only in a brain, but there are other areas which fall within this intensity value range, and then they get painted. So then what you can do is maybe you tune into, you are satisfied with certain values, and you can go and erase the rest of the stuff. So yeah, so if I say confirm, so then I have this one, and I can again go to the paint tool or eraser, and I can erase the elements in which I am not interested. For example, I just erase this voxel that version. This is how the manual segmentation is done. So segmentation is mainly, so all of these voxels have so this creates a binary mask. These voxels have some value which is being rendered as a color here. And that value could be 1 or maybe some value like 8 or 10, whatever is being used, and then being rendered as a color here. So now coming on, so we already saw image thresholding, then there is graph cut. So graph cut, what happens in graph cut is that this complete image can be considered, one can create a graph data structure from it, where node is a voxel, and then the intensity value is like the edge weight. So that is how you can create this weighted graph, and based on that, you can run graph algorithms on this image to segment certain part of the image slice. Max and mean flow cut algorithms are used. You can search for graph cut methods in segmentation by Boykov. It is quite popular. So okay, here also I believe we should be having it. For example, there is region growing tool. I think it is based on graph algorithm. In region growing tool, we just pick certain seed value in the area and then it grows. I think it's not graph based. It just checks for the neighborhood, and then if the intensity value of the neighborhood is same, it just keeps growing. So yeah, that is region growing. And then coming on to the active contour. So we already saw the contour drawing, but what is active contour? Let us see that. So also called live wire. So let us say that okay, I create a new mask, and I will T1. Okay, I'm just now, I've created a new mask. I will operate on it now, and I will show you what is the live wire. For example, I want to segment out, say, or maybe here, this region. So as I start, so it snaps to the intensity value by itself. So I'm not actually drawing and accurately in that area, but based on the intensity values, it just tries to snap to the boundary where there is a variation of the intensity value. So it tries to go find a minima and then itself create the boundary over there. So this is called active contour. Yeah. So it allows you to do segmentation much faster. And then once you are done, you can just say confirm segmentation, and then this gets painted. So here the image intensity values were being used automatically to create a contour. So this is what we discussed about the semi-automated method, and then there are automated methods. So I can just talk about these methods, but I do not have these models to actually show you. I can provide you links which you can use to run the automated segmentation. The first one is a template based. In a template based method, there is a base model or the template model which is morphed to fit to the image data. And then that is how finally you have the a new model that is according to the given data. So you have already a base model that you morph to produce the surface. Statistical model is based on statistical modeling, where a number of data sets have already been used to create a statistical model, and then that statistical model is fitted to the given data and produce the segmentation. that is statistical modeling. And then deep learning, you already, I believe you are aware about this. Convolution neural networks or very popular segmentation method used in medical imaging is UNet. This UNet is used to first so you have already done the manual segmentations. So one would use these semi-automated and automated tools to create labels, and then train the model, and then given an unknown data uh, based on this a priori knowledge that you have in this convolutional network, this by virtue of this model training, you will be able to get the segmentation output. So there are, if you search on internet, you will be able to get a lot of open source, open implementation of UNet. Statistical modeling is also available from SEI, Utah, and template-based method. I believe there is something called Free Surfer. That is a template-based method. It allows segmentation of image brain. It's from, I believe it is from Stanford University. Free Surfer. You can search on internet. It is also a very popular tool used for brain image segmentation, and it has quite a good accuracy. It has sort of state-of-the-art accuracy, and many deep learning algorithms are actually benchmarked against Free Surfer output. Now they are also venturing into deep learning, and Free Surfer is also providing deep learned model to do the automated segmentation. All right. Now, once we have the segmentation done, so yeah, this is just a snapshot of live wire. I've already demoed it to you. We would like to create a surface out of it. The surface reconstruction, one of the most popular algorithm is the marching cubes. We will discuss that. We will not be discussing the dual contouring or Delaunay-based approaches to create the surface. Yeah, so we'll discuss in the for the slides. I'm going to talk about marching cubes. But before that, let me just show you the segmented mask already, or segmented image already. So the SCI, if you go to the same website, they have also provided a segmentation archive as well, which is a nerd file. And if you open it here, it is just the segmented. So they have already given labels to the various parts of the brain anatomy for this given case. Maybe I'll just do some color map. I will use multi-label. So now you will see that they have, for the cortical area, they have some label, and for the internals also they have different labels. Yeah, likewise this. And then yeah, this is the complete segmentation that they have already done. And then if you click here, you should be able to see the pixel value. It is 8. So this means that this voxel has been assigned 8 8 label. And say if I click here, so you see that this pixel value is 3. So all of these voxels have label 3, and they constitute one component, and that is segmentation. All right. So if you have downloaded data, you can see this as well at your end. Now coming on to surface reconstruction, we will talk about marching cubes. But just to simplify matters, we'll first discuss about marching squares, which is as a two-dimensional variant of marching cubes. So let us say that we have an image, and this is an object that is which was actually there, and now this is within the grid, and we would like to run the marching squares. So what marching squares does is it would run. I'm not sure if you are already aware about this algorithm. It is quite popular, so maybe you are already aware, but for the sake of completeness, I will discuss this algorithm. So this you can assume that a square is marching from left to right and then so on for next row. It keeps on going. As it crosses the various parts of the image, there are different constellation of pixels observed. So they could be like this, that the square is completely inside. So then each of the vertex is, so here red means that it is within the object, it is colored. So like this here. So it can be completely inside the image, or it can be, so it could be this constellation. So it can be completely outside or inside. This is the uh, first constellation or first order of these pixels. And then next could be that there is these are the two image pixels or the object pixels. Then you draw a contour like this. And if they are on the opposite edge, then you draw two contours or two lines like this. And if it is only one pixel inside the object as the marching square goes through it, you draw only one line like this and so on. So based on the orientation of these pixels, you draw lines in that square. Now this line is usually drawn. So what should be the location of it? It is usually the, if we are using binary mask, then it is the average value. So it will be passing to the center, 0.5. So if the binary mask has a 1 is the inside label and 0 is the outside label, then 0.5 will be the average of no 0 value and 1 value. Then this line would be passing through the center. So now coming on to our actual image. So we have, so here we are showing the highlighted pixels or in this grid. So the object is, so these grids define the discretized object. And now as the marching square goes through it, it will draw lines here, here, because only these two voxels are inside. So these two pixels are inside. So it will construct an edge here. Here, let's see the orientation here. So there are three voxels that are inside the object. So we will construct an edge here. So likewise, as it crosses through the through this image, it will construct these lines. And ultimately, this was the actual object, but you had this voxel pixel representation, this discrete representation, and then you want to create a continuous object from it. You end up creating this kind of object, which is an approximation of the actual object. So yeah, so what happens in case of marching cube is just that instead of lines, triangles are drawn in the cube. And let's see a demo there. So if we just extrapolate it to the 3D space, maybe I'll just, okay, let me show you this video of marching cube. Okay, sorry, this is some ad. All right. Okay, so you see here marching cube. So we have this kind of object, and then as it, so instead of marching square, we'll have a marching cube. It marches through the mid volume and it will construct triangles. So this is all about the marching cube. Yeah, so here the different constellations. So now in case of square, there were only so if there are two, there is a possibility of 2 raised to power 4, 8 possibilities were there, but here we will have 2 raised to power 8 possibilities. And then different triangles can be created like this. So if they are falling within the image or outside the image. So this is the gist of it. And then you have a surface finally. So here it is of a higher resolution. So ultimately you will get a sphere, which is a triangular mesh created as an output of the marching cubes. So this is called isosurface reconstruction using marching cube algorithm, and this algorithm is quite popular. Now, what
Sir,
happens
I
is
have
that
one question.
yeah.
That how does a marching cube gets to know that what portion has to be taken and what has to be removed out?
Yeah, so likewise, so if you just imagine that, so here in this example, the voxels were not of different intensity. For example, we have this mask right here. So then the cube will pass through this mask, and it will, if it is totally inside, then nothing is constructed, but only at the edge boundary, there will be different constellation that inside voxel intensity is different and the outside voxel intensity is different. So then it has based on, so maybe I'll show you different link. It is also available on Wikipedia. I'll just show you some photographs. So maybe it will be, yeah. So likewise, this we were discussing about these marching squares. So here we will put triangles. For example, when there is only one point within the image, so we will add this triangle there. If there are two voxels that are one intensity value, so I will add this kind of triangle. So the Robert Klein, who is the actual implementer or inventor of this algorithm, he came across through these possible orientation, and rather others are like reflection of this these possibilities. So we do not consider all of the possible permutations. We just consider only these permutations because others are like reflection of it. And then based on that, you keep on adding triangles as you cross to the voxel.
Okay.
This is
And
how
how,
the yeah.
how the points are being observed using the images that what
Yeah,
we process.
the image, using the image. So using the
All 3 to 4 images together.
all three. So yeah, as we discussed earlier, that this is a 3D scalar field. So which is like a cuboid, and which is made up of small cubes. So as I showed in this presentation here, so it's like a cuboid, and then a cube traverses through this area, and then this has some intensity value. So we'll check for the intensity value at these corners, and then based on that, a triangle is constructed in this area.
Okay, okay.
So it keeps on going through the, so as now just going here. So if I want to construct this surface, I'm in here, multi-labels are there, but usually you paint only one area. So then the inside will be some label, a non-positive value, the outside is 0. And then the cube will, near the boundary, it will see all of those possible constellations or permutations of the pixels, and it will keep on adding triangles of that orientation.
Okay.
So it will not be exact, it is just an approximation, but it is quite fast because it can be parallelized. This algorithm can be parallelized, and that's why it is quite popular as well.
Got it, sir.
But
thank you.
yeah, I hope the answer was clear, but you can very well, if you want to go into details, as well as public implementation are available for this marching cube algorithm. Okay, so
Sir,
let
may
us,
I?
yeah.
Sir, the point cloud which we are making over here, I believe that if you are going with a more resolution, it will be required to have more computational time as well as complexity. For
That's right.
real time implementation, it will be a problematic. So, is there any way we can reduce the vertices over here?
Well, yeah. It's a very interesting question. Yeah, it is not real time. And also we are not expecting it to produce these surfaces in a real time way. We create these surfaces beforehand. Then once we have the surfaces, then we use these surfaces for rendering and visualization. So it is not required to have this real time. First that. Second, coming on to the resolution. Now resolution is a very tricky part. Resolution implies, in case of CT scan, that you are so let's see this only. You are giving more radiations to the patient. So if you want higher resolution, then have you will take slices at much nearer to each other, so that
Yes,
there
number
is
of
lesser
slides.
gap. Yeah, but what happens is that due to increase in number of slices, you end up giving more radiation to the patient. So these radiations are cancer causing, and we cannot do so. So that is a problem, that we cannot increase the resolution of CT scan to much detail. There are recommended resolutions by all these scanning machines, and they use that only. So that is it. And also we avoid taking CT scan of a patient very often.
Yeah.
MRI is fine. MRI is magnetic field, but CT scan, the X-rays are ionizing radiations and cause cancer. So uh, it is better to not increase the resolution to larger extent. Sometimes if you want, say, higher resolution surfaces, we want it, then in many times it is done for cadavers. So for dead
Yes, sir.
bodies, they will have higher resolution scannings available. And you will also see that in MRI, you might have seen these 1.5 Tesla, 3 Tesla, or 7 Tesla. So actually, that is going to increase the resolution of the image.
Yes, sir.
So yeah.
Yes, sir.
So
Sir, further, I want to add something.
yeah, please.
Sir, the image which you are taking over here after rendering, this data we are getting in a VTK mesh format.
Oh, okay. So this format is usually software specific, whichever software you are using. So I'll go to that step and I can show you what format
Yeah.
I can
Yes,
produce.
sir. Yes, sir.
So next step will
Thank
be
you.
that. Okay, so here I'm showing, so as you discussed about the resolution, so when we run the marching cube algorithm, there are artifacts observed. These are uh, because marching cube runs as this cubes, so you see this staircase artifact just because of the nature of the algorithm. And also we have discretized the space, and it is not the continuous domain, and then we are reconstructing a signal. So it goes through aliasing. So it's mainly aliasing effect in 3D. And then this results in this kind of surface. But actual bone shapes are not like this. So then this results in that we need to do the mesh processing, post-processing operations. So that is our next topic. So on the right hand side, you see that this looks like more like a bone. So it is a talus bone that is at your ankle, and it is smoother and looks like a bone, but the left hand side isn't. So I'll just go ahead and show you it in this MITK. So we have these segmentations. I will. So it's different data types. So I'll convert to. Okay. Okay, now we see this create the polygon model. And if I hope it doesn't take much time. If I say create polygon model, it is creating the polygon model from it. So since there are multiple labels, so it is creating multiple polygon models. Okay, you see the polygon models got created. There were say 8 labels in this image. So we have 8 surfaces, and I see it here in the. So let me remove this crosshair. Now we have the surfaces, and for example, yeah. So this one is for the brain, internal brain, object 4. Now you see that this is actually a mesh, and we can do remeshing operation, but let's not do it here. I'll use a different tool. Now I can export it. You can save it. Now you can save it as a VTP polydata, or there are options like STL format or PLY format. PLY format is the best format, I believe. And I'll say I'll download, export this brain as a PLY file. Now let's just go back and see this PLY file. Now I will open this PLY file in Mesh Lab, which is a mesh processing open source software. And I have the brain here. So I understood that actually it is looking totally black because the normals are inverted. So I'll go and invert the normals. Normalize face, invert face orientations. Yeah. So now I have this surface. This is the brain surface. You can see that because of this marching cube algorithm that ran, we have this staircase artifact. And if I enable the triangulation, you can see that it is actually a triangle surface made up of all of these are triangles. So now in order to remove this artifact, a lot of post-processing operations are done. One of these is a smoothing operation. So we can run the Laplacian smoothing is a very common smoothing, and I will say run 3 iterations. I'll do apply. Now I applied it, and you see that now the surface that is generated is much smoother. Still, there are staircase artifacts you can smooth further to produce a more realistic surface. But however, as you smooth more, the mesh contracts and the volume contraction is observed. So then there are a lot of algorithms in smoothing which preserve the volume of the mesh. So there are volume preserving smoothing algorithms. What they do is after smoothing, they push back the vertices with respect to the original position so that you have a smooth surface, and then the original position is maintained. Then sometimes you are not interested in those many triangles, but you don't want to lose this geometric information. One can do the remeshing. So remeshing, there should be a remeshing algorithm somewhere here. Yeah, remeshing, isotropic remeshing. I will do remesh and iterations 3, whatever. I'll just keep the default values and apply. It can be time consuming. There are too many triangles here, and it can take some time. Maybe I'll go to the slides and we'll come back while it is done. Yeah, so we discussed about that the marching cube output is not smooth, and then we want to produce the smoother surfaces, and that is why we do the mesh post-processing operations. They are usually smoothing or remeshing. Yep. And then just wanted to share with you what all possible software that you can use for creating segmentation and then creating surfaces. They are software Mavis Lab from Germany. Blender is also very popular tool, mainly used for animations. And then Mesh Lab, that the one that I was using, and ParaView from VTK library guys. So they also have a segmentation tool that is called 3D Slicer. You can use that to create segmentation, and ParaView to perform various mesh processing operations. Okay. Ultimately, we'll have all these surfaces, and then we need to render it realistically. So usually that rendering needs various surface illumination models and also applying textures to these surfaces. Generally, the textures, in order to create realistic renderings, the texture values are taken from the uh, actual medical data or photographs and then applied to these surfaces in order to produce realistic rendering. Sometimes realistic rendering is not required. For example, for teaching, maybe realistic rendering is not required, just this illustrative rendering is required. Then they have usually they have some template colors that they use for certain organs. For example, arteries have red color, veins have blue color. So red means that oxygenated. So they will use the red colors for arteries and blue for the veins. Similarly for other organs. So let us see one. So I have this link where they have ultimately produced a 3D model from surfaces and okay, if yeah, so just want to show, so the remeshing is done. Now you can see that the triangles are reduced this and are also isotropic. So they have usually same neighborhood so size. So one node has 1, 2, 3, 4, 5, 6 neighborhoods. So this sort of isotropic remeshing is sometimes useful for various algorithms down the pipeline on meshes. So we discussed about smoothing and remeshing in order to produce smooth surfaces. Now let us see a final outcome which can be produced by this all these stuff that we discussed. Okay, here it is. So here you see a 3D model of brain rendered, and it is being rendered realistically. So here you have this cortical surface that we segmented just a while back, but it is of better quality. And but over the top of this surface, they have added textures. Now let me show you the rendering. See, it is also a triangular surface, and these vessels are also made up of triangular meshes. And then this can be rendered realistically by applying textures. The textures are shown here. For example, normal map, roughness, scattering, translucency. These maps allow us to uh, render the objects realistically. For example, I'm just using this matte cap surface, so it looks like a metal now. Yeah. So going back, so I have this rendering, and then this can be used by the students. If they want to see certain organ only, then they can disable the visibility. For example, here vessels are disabled, arteries are disabled. Likewise, a surgeon can then, or a teacher, a medical practitioner can discuss about this 3D model while talking about where to operate, what happens in the operation, what is the natural anatomy, what is the pathological anatomy, that is the disease anatomy, what happens there. So this allows to share the information in a better way. So this is an atlas. Again, it is open, neurosurgicalatlas.com. You can go and actually see it. I can share the link in the chat. Okay, there is a question. Is it possible to convert STL file in VTK? STL file in VTK? I mean, you want to convert it from STL to VTK? Yes, it is possible. You can use a ParaView software that allows you to load the STL file, and then you can save, export as an VTK. Even this MITK, we just saw that it allowed to save in different formats. So you can load it in the STL format and export it as a VTK format, VTP format actually. So it's a polyhedral surface that is VTP. VTP is used for it. Okay, coming back to the presentation again.
Sir, we also have a one question from Hitesh Divanshi ma'am. It is in chat box.
In the chat box. Oh, okay. Hitesh, sir, I have to. Okay, you mean these questions? Hitesh Divanji. I
Hitesh
have to guess.
Diwan.
Yeah,
Hitesh.
so they are working on brain tumor segmentation and chatbot who answers by learning image training can be done from available. How to test the developed model? I have to brain tumor number one brain tumor chatbot who answers by learning and image training can be done from available. How to test the you want? Okay, you mean you want to test the uh oh okay, so now you have done the tumor segmentation. I'm not sure what you want to test, but you can use free surfer or there are multiple atlases that are available over internet. Maybe you can compare it with uh, the actual annotations. So you need an annotated data and then you can tell that whether which or part of brain is it, but I don't understand the actual question.
Okay,
Training
sir,
can. Hmm?
I have a question that we have available data set for both the definitions, but now
Hmm.
we have trained the model.
Mhm.
Now we need an unknown data set which would tell us whether our trained model is good or not bad.
I see.
Go
Okay.
to doctor, they don't give us because it's privacy or secrecy. They cannot give it to us.
Yeah, okay. I have an answer for that. There are a lot of open source dataset available, and I can share with you this conference that is going to happen next week. And here you'll see that there is a session by Jan Viska who will be talking about the primer on biomedical data sources. So perhaps this session might be of interest to you, where he will discuss about open data sets of various organs. But yeah, I believe there are quite a number of open data sets available. There is another something called Medical Grant Challenge by Mikai. Medical Grant Challenge that is hosted by or double C, I am forgetting. You can search for this, and then they have quite a number of challenges related around uh, brain tumor segmentation or brain segmentation. They provide both test data sets and the training data set. You could possibly use it. They have quite a lot of data. I hope that should help you.
Maybe I'll try.
Yeah, you need to search, and then maybe you'll be able to find.
Mm-hmm.
There are more questions. There is some form. Okay, it's not a question. Okay. Okay, now it's 8:43 and we have like 45 minutes left. Maybe we'll take a 5 minutes break again and come back. So we will meet at 8:50. All right. So then we will continue for 40 minutes.
Okay, sir.
Okay, sir.
Okay. So now we will discuss the rest of the topics. Mainly, we have left the volume rendering, and that will be last topic and should get completed in 15 or 20 minutes or so. I'll share my screen again. All right. So, yeah. So just some concluding remarks on surface rendering. So it is used for medical education training, but surface models, and you can create volumetric models that can be used for biomechanical simulations and can be used for rapid prototyping. Generally, these surface models are triangular meshes and derived from medical images. The raw surface that we create using the marching cube has artifacts, and then we have to follow up with smoothing or remeshing operation. And also we need to be very careful about the accuracy because these operations change the shape a bit. So we need to consider that volumes are preserved, and it also involves a lot of manual steps. As you observe that even the segmentation, there can be difficult cases that cannot be segmented automatically. Then you end up using the paintbrush tools and also the semi-automated tool like thresholding if you want to. Uh, Many times the automated segmentation algorithm undergo user supervision. We cannot totally rely on automated segmentation algorithms. So a user will actually go through the segmented output and correct it and then finally create the surface. So still it is time consuming, and also later on when you have surfaces, in order to create the realistic rendering, you need to create textures and determine the BRDF. Determining BRDF of the actual surface is also quite a challenge, and a lot of effort is being going on in creating realistic rendering. You can search physically based rendering techniques. There is PBRT book available online freely, where the main aim is to replicate the actual physical phenomena of light interacting with the surface in order to produce the realistic renderings. A lot of hacks are done in computer graphics to produce this realism so that the application remains interactive. One of the main reason why surface rendering is used because the graphics rendering pipeline is implemented already for these surfaces, triangular surfaces, and the rasterization pipeline. So that is why uh, once your surfaces, you can interact with these rendered surfaces very fast. The next topic is volumetric rendering, uh, which is quite computationally intensive, and now uh, again now the graphics card have been developed specially for to enable volumetric rendering. All these efforts or these GPUs were actually invented for this graphics processing by virtue of this gaming industry. In gaming also, you see that those are actually a game need to be interactive. Then that's why they have the surfaces. So all of those are surfaces actually being rendered in 3D scene with realistic textures. Uh, so all of this innovation happened for gaming or for entertainment. Then now these GPUs are being used for machine learning and deep learning. Yeah. Coming on to volume rendering. So volume rendering again can be used for training and also for radiology in order to check certain diseases, for example, brain aneurysm, or also for tumor infiltration. So uh, 3D renderings can be used to check how much tumor has grown or infiltrated the nearby tissues. Okay, could you please mute? That can happen in online meetings. Okay. Can
Prajapati sir, please.
Krishna, mute all.
I think there you. Okay, now I will unmute myself. Thank you. Yeah, also for the therapy planning. So the where to give the dose during this chemotherapy or the radiation therapy. Sorry, the radiation therapy. It should be localized at a certain area and should be enough as well. So these visualizations are used for therapy planning. There are even MITK has, I believe, certain plugin for therapy planning. Also, the difference between direct volume rendering or surface rendering is that in surface rendering, you need to create a surface in order to render. But in direct volume rendering, you do not need a surface necessarily. If you have surface, then of course you can use this surface to, or if you have labeled medical data, you can use it to, in a better way, render the volumes, but it is not necessary. That is why in many cases the patient specific renderings, if one has to do direct volume rendering, is used, as creating surfaces can be cumbersome. But with the advent of deep learning and all, this time has already been reduced, and I believe in future surface rendering um, would be much easier, as well as there are innovations in the volumetric rendering side now that allow to uh, vo- render the objects using volumetric rendering in more realistic and in a fast way. Whatever animated movies you see uh, that are rendered volumetrically, they use volumetric rendering or physically based rendering, could be surface rendering as well. There a lot of time, they already have quite a lot of time. They do not need real time behavior of the application. They can just dump an image generated by this rendering and create the next frame, and so on a movie is made. But for our case, if you want it to be interactive, there are a lot of tricks done in graphics pipeline. I mean, in using graphics pipeline to render it in a fast way. A lot of innovation has been done by companies like Siemens and Philips, and one of the state-of-the-art for volumetric rendering called cinematic rendering is by Siemens. Okay, coming on to the very basic of the volumetric rendering, there are many variations in volumetric rendering in order to make it fast, in order to how to use the graphics hardware to accelerate or reduce the time being used to render a frame. But we are not going to do that. It is out of scope. It is quite a huge topic in itself, and a lot of research is going on. So we'll just talk about ray casting currently, which is in its simplest form. What happens is that a ray is thrown from the image to the volume, and then it passes through the surface, and based on this interaction with this media, a color is generated. So the ray casting principle, view rays are traced from the viewpoint through the volume. It interacts. So here the media is participating in rendering, and this accumulated color, which is based on its opacity or its, I mean, how dense the object is, how transparent the object is. Based on it, you will eventually see a final color. So that is the idea. But this is very simple way. If we consider more, then there is ray tracing, path tracing, and also global illumination, where uh, the lights falling from other objects, like there's assume that there was another object, and from there, and the light is getting reflected from that object onto this object. So then that makes it very complex. It becomes a recursive nature of the physical phenomena, and Monte Carlo methods are used to render this. So ultimately, so as we discussed earlier, so we have this voxel grid, and array would be, so assume that here is a voxel grid you are looking at from the top, and then uh, from the image plane, from one pixel, array is thrown. to this volume, and then the color is computed. So this is based. So we there is a very popular paper from Katya that explain the rendering equation, that is like the basis or foundation of the rendering, and we will discuss a very simplified form of that rendering equation used for volumetric rendering. There are multiple phenomena that happen when light interacts with it. There is emission, absorption, uh, and the mix of these, scattering. So all these phenomena, if we want to render it realistically, and if we want to model all of these phenomena, the implementation or the solution will be quite time consuming. So many times simplified models are used to render the objects realistically. Now, as we observe that these are voxels, but a light ray that is thrown from the image plane that can intersect this voxel at any position. So in order to find the value at certain position, trilinear interpolation is used. For example, if it is we want to the light ray is intersecting at here this position, then we can trilinear interpolation is nothing but, for example, linear interpolation can be represented as like this. Where x is the value where we would like to put the point, and once we have interpolation here, and then with the two lines it becomes bilinear, and we add the third line, then it becomes the trilinear. So trilinear interpolation is used. It is quite popular. There are other interpolations as well. Then we will have some average voxel value here, or some uh, intensity, or we will find the interaction of the light in this position. And how is it done is that we will have a transfer function. That transfer function will tell us based on the intensity value of image what color and opacity is here available here, and then that is used to render the volume. Now it is based on the rendering equation. Rendering equation, this is a simplified version of rendering equation, volume rendering equation. Here we have an observer, and the light is traveling like this, and it gets absorbed and emitted along when it's traverses through it. So this can be represented as this integration equation. On the left hand side, you have the intensity value that is observed, and then this is a decay function by the attenuation of which tells the attenuation of the light that happens, and then the c lambda is the lambda is the wavelength, and here c lambda is the reflected or emitted light at point S, and it traverses from so x is the location and r is the direction. So at x position on the image plane viewed in r direction, and for certain wavelength lambda, for length L, if the ray traverses length L, then and S is the current position of the light, and then the total intensity observed can be represented by this integral equation. Now, the discrete representation can be written as Riemann sum. So here, we are representing the same equation as the yeah, you can. I believe if you have studied the numerical algorithms course, there in numerical integration we discuss about the Riemann sums. Um, any integration can be represented as the sum of these triangles, sorry, rectangles, and so that is how in discrete space we integrate. And here this Cx alpha I is actually in this equation denotes the color at position xi, and alpha is the opacity. So after we multiply, so this tells you how much it has traversed, and then this color and opacity we get it from the transfer function. The transfer function is nothing but It is a mapping function that gives us the color and opacity value based on the intensity values. So I will just show you the application as well in MITK. So here is a transfer function. So this is the histogram of image, and then it is giving red color to this vessel for so intensity and color. Yeah, so and the transparency as well. Only to the voxels that are within this intensity value range, they get the red color with certain opacity. So this is the transfer function. Now in this image, so I took it from a thesis by a person who has worked in neurosurgery rendering. I will be adding references later on. That section is not populated completely, but here you can see that volume rendered at the original intensity values, grayscale, and then at some constant opacity, and then with the volume rendering transfer function. So this looks more realistic. So we'll see it in the application as well. Let us go back to the application. Yeah, and we will remove this. So we don't need these surfaces and even the segmentation. So now I have just the data. Yeah, medical image data. So we discussed that the difference between volume rendering and surface rendering is that we do not need segmentation. So in MITK provides a volume rendering plugin. So I selected the image here, which is the MRI image, and then I will enable volume rendering. So you can see that even though I did not create any surface, I can see the 3D visualization. How is it possible? Just because, and also here is the intensity values of the this 3D scalar field. So on the y-axis, so it's called histogram. On the y-axis is the population of voxels, the number of voxels that are of intensity value 0. And yeah, so like this. So at any location, this bar tells us how many voxels are present of that intensity value. Now we are using this transfer function. This is transferring the voxel values that are within this curve, below this curve. So all of these voxels with these voxel values. So we are excluding the voxels that are outside. So we are totally excluding the dark voxels, black voxels, which is outside of the image. So that is why it is starting from here. Then it goes like this. We will change this transfer function and see its effect. And then it is applying the color that is provided here and also the opacity. So opacity here is 1. We can change the opacity to say 0.8. So this is what is happening. So let me make it 1 back 1. It was 1. Oh, looks like if I give some value, it is, yeah, it becomes opaque and then you see the complete cuboid. But with, I think it is taking internally some opacity. 0 should make it completely transparent and we shouldn't be seeing anything at all. Okay, now let us, maybe I'll just use some preset. So usually they provide some presets of these transfer functions. For example, MRI generic. This is an MRI image. So I'm using the MRI preset. The curve has changed a bit. Let us see what happens if I interact with this curve. See, as I start adding the voxels that were of 0 intensity, the complete area is getting filled. So I'll just bring it back here. Also, if I change it further, so different areas are, let me maximize it. Yeah, so different renderings are observed. as I change the graph of this transfer function. So this actually changes that in that equation, it is changes in changing the color and opacity value. As I see from my screen, I'm looking towards it. The rays are being casted onto the volume, and then I see a certain so ultimately it is getting transferred onto an image pixel value, but it is happening by virtue of this ray going through this volume, interacting with these voxels, and then picking the value of a voxel based on this transfer function. You can use different transfer functions. There are multiple transfer functions available, but for MRI, we use the generic. You can create your own transfer function and use it. Here we are using, say, I am using CT bone, but MRIs are not meant for showing bones. That's why certain values which are following in that bony values are being rendered, but it is actually not bone, it is skin. We could actually use this bone for the CT scan. I'll load the CT scan data. Here is a pseudo CT. Now I do the volume rendering for this, and then I use the CT generic. Now you can see that I will disable the crosshair. Now you see the skull. So without creating segmentation, one can see these surfaces by virtue of volume rendering. So this is all about volume rendering that we wanted to cover. It is quite a huge topic, and you can study offline. Now coming on to some final remarks on volume rendering. It requires, so designing transfer function is quite challenging, because how would you tell that which voxel intensity corresponds to which tissue? So it is in itself a research area and also there has been quite a lot of work in automatically finding these transfer functions by deep learning. Or so you can see on internet there are some research papers in that direction. It is used quite a lot in patient specific visualization, but as it doesn't require any special manual steps. The only manual step is sometimes creating those transfer functions and then tuning the transfer function, as we were doing with that UI, by changing those points. Now it can be less accurate. The issue is that many times the MRIs are not standardized. That is, the voxel value that you receive from different scanners can be different. Then the same transfer function will not be able to work. CT scans are still standardized. I am forgetting the paper that from which I'm quoting here, but I read it in a research paper that MRI's scanning machines are not that standardized and end up producing different intensity values for the same object or same subject. Yeah, these outputs cannot be exported because these are not actually surface models and cannot be used for 3D printing. It is computationally intensive. If you want to make it more realistic, it becomes computationally intensive. And also, there is still one of the recent papers of 2016 is by guys from Siemens. They showed the cinematic rendering, which produces more realistic models of medical data using this volumetric rendering. So you can read about volumetric rendering. Here are some snapshots of volumetric rendering. They look slightly more realistic. Yep. So this, let us now see maybe, so it is the final concluding slide. We will see a system of a virtual reality system where volumetric rendering is being used. I am not sure if I can, we should be able to hear the sounds. Mirror my video camera. How do I share my sound as well? If I let me play if you, and please share with me if you are able to hear the sound as well. Okay, it's not opened. I need to open it again. So, are you able to hear anything?
No, sir.
No sound?
Include the system, system audio.
Okay, yeah, I wanted to include that. How do I here also? Maybe I'll choose the, and then the device settings, audio devices, speaker, microphone, video settings. Let me try again if you hear it now. Can you hear it?
No, sir.
No, sir.
Then I don't know actually. Yeah, then maybe you just you can actually watch it at your end later on, but yeah, I can explain what I hear, and you can see it. So okay, so here the person is explaining that he's from certain university in Europe, University of Basel. They have a virtual reality room, and then they have this virtual reality this HTC device to see the virtual renderings, and this device allows them to maneuver with the this 3D data. Yeah, you can see the subtitles. Please read the subtitles. I believe that will help. Yeah. So you saw that I believe you read these subtitles. So the volume rendering that I showed didn't have any shadows and all. So it didn't have any global illumination behavior. Here, the person is also showing that with the addition of shadows, you get the more realistic rendering. Yeah, so a lot of work is going on in creating realistic rendering and integrating that in the virtual reality systems. Ultimately, the rendering is like foundation, and then these are like devices that are used to interact with these rendered volumes or surfaces. So this is all about volumetric rendering. With this, I close the session, and now we can discuss any questions if you have. Thank you for your attention and your time. I hope I was useful. So maybe I'll see the chats if there are any questions. Can MITK be used in edge computing with low memory devices like Jetson Nano 2GB? What is the meaning of edge compute? Okay, edge computing. You mean the edge devices? Can MITK be used in edge computing with low memory devices like
Yes, sir.
Jetson Nano 2GB? I believe, yeah, I think you might not be able to do the volumetric rendering, I believe. In fact, there is one thing that you can observe here. It shows the memory being consumed by the application. So here it is using 415 MB. So based on the data set, if you add very huge data set that itself is in GBs, then you won't be able to use it at all. So you should be careful about the size of the data set itself, which is loaded in the application. Then some memory is taken by the application itself, and then the memory by the more renderings that it creates. So if we add more data set like surfaces, so that all the surfaces take very less memory as compared to the volume, the CT scans. So most of the data is the memory is taken by the images. So if you have small images, then I believe you should be able to run it on an edge device.
Actually, sir, my model size itself is somewhere around 1.5 GB, the lowest size of the model.
Okay.
That's what I was thinking whether I can be used, because I tried some other methodologies and I'm not getting it done in a proper amount of time. That's why I was just looking for the alternative, sir.
Yeah. So your is the are you using images or you're using surfaces?
Sir, I'm of course I'm looking for segmentation over there.
Yeah.
As well as I'm looking for the surface also.
Okay, so is your edge device doing automated segmentation? Is that why that's?
It's fully automated, sir.
And then you need both images and surfaces.
Yes, sir.
Yeah, then I believe you need to. You can maybe work if you can work with reduced resolution images. So there are deep learning methods that can even produce good quality surfaces even with the reduced resolution of images. So possibly you could use that model in order to then create a surface or segmentation by reducing the images. But I don't know. I mean, it just a way out. But ultimately, memory is going to be a crunching issue if your data is in GBs.
Sir, actually, presently I'm using a VEDO library for VTP files, and with that I'm rendering my surface and trying to make the model.
Which library?
VEDO.
VEDO.
Yeah, it's a VTP based surface rendering method.
I see. I am not aware of that. Yeah, you can check with MITK. I don't know.
Yes,
Yeah.
sir. Thank you, sir.
But usually the constraint here is the medical data size itself, and then some memory will be consumed by the application.
It is, sir.
So I
Yes.
would, yeah, okay.
Thank you, sir.
Thank you so much, sir, for such an interesting session about visualization in the medical field. It was very interesting to learn about all the tools which can be used. Now, I would request everybody to please switch on their cameras for a group photo.
Yeah, I think I also need to.
Yes, sir.
Yeah, I hope you all got fair idea about the visualization, and you can then explore more in this area. It is quite an active area of research, and actually with the with so much of interest in deep learning, there are very few people who are working in this area. Yeah. But now,
Thank you.
yeah, I'm just stopping you again. So, but now a lot of neural methods are being used for rendering. Something called neural rendering is also a very hot field.
Yes, thank you, sir, once again. And I'd just like to inform all the faculties present here that the test related to this week's session would be conducted on next Monday. So please keep that in note.
Or will there be a test for it? Okay.
Yes, sir.
I hope I do not need to set a paper as well.
Yes, sir. Okay. Thank you.
That done? Okay. Then we are in time.
Yes, we can
Yes, sir.
complete.
Yeah. If you have any concluding remarks, not especially any question, you can just say we have just 4 minutes left. Otherwise, goodbye from Gurgaon.
No, sir, it's okay.
Yes, sir.
Thank you.
Thank you. Thank you so much for your time. Bye.
Thank you.
Thank you, sir.